Okay, this is section 4.7. The I can statement, or the objective for today's lesson, is going to be find a function model based on data. So we'll write the word data right here. So that's what we want to do. We want to take some data and figure out, hey, what's the best mathematical model that I could come up with for this? So in the warm-up, we've got a little picture right here. This is the first figure, second figure, third figure, and fourth figure, and so forth. And what we want to do is we want to figure out how many cubes will be in the 10th tower and how many cubes will be in the nth tower. So kind of a numeric example to start off with, and then a little bit more of an algebraic example. So let's just count them up. There's 3 right here, and then let's see, 3 plus another 2 would be 5, and 5 plus another 2 would be 7, and 7 plus another 2 would be 9. So it goes like this. So we're talking about 3, 5, 7, 9, and so forth. That means the fifth one in line would be an 11, and the sixth one in line, of course, would be a 13. So we'll just kind of list them like that. And what we want to do is we want to figure out there's got to be some relationship between the input, like counting which one we're on, and how many blocks there are in this tower. One thing that can be helpful is to think back when you talked about sequences, maybe in a previous course. But if we were to follow this pattern backward and say, hey, what would the 0th one? That's kind of a weird way to talk about that. But if we didn't have any, if we hadn't started the pattern at all, if we hadn't done the first one, second one, and so forth, what would it have been? Well, there would have been only one block in that one. So we're looking for a pattern that goes 1, 3, 5, 7, 9, and so forth. So it's basically just the odd ones. So this would be kind of asking, well, what's the 10th odd number in this list right here? But we've got to start right there. So this is a little bit tricky to figure out sometimes. Again, you might think back on how you did sequences and everything. One thing that we'll notice is that if we plug in 0, we should get a 1. And if we plug in a 1, we should get a 3. Well, it's going up by 2 every single time. So if we do 2 for the amount of increase every time, and we find some relationship between this, again, different ways to do this, but what I might do is say, hey, if I take a 3 and I double it, that would give me 6. And then if I just add 1 more, then that would give me 7. So what I'm going to think is I'm going to multiply 2 by 10, and then I'm just going to add 1 more. And let's just see if this pattern would work for, let's say, the 5th one. So if I did 2 times 5, so we're kind of predicting that should be an 11, and I add 1, I end up with, let's see, that would be 10 plus 1, so I end up with 11. Okay, so we're in good shape there. Let's try it for the 6, 2 times 6 plus 1. So that would be 12 plus 1, that would be 13. So I think this is going to work. We're going to end up with a 21. Okay, so that's how many there would be in the 10th tower. Well, going through a process like this is a little bit hard, and we're going to talk about easier ways to do this. And again, you might remember something from previous courses about sequences. But basically, the rule is going to work like this. We're going to do 2 times the number that we're on. So if we wanted the 50th one, we'd plug in a 50, and then we're just going to add 1. So this would be the formula that would produce that. And that actually is an arithmetic sequence. We start at 1 and go on like that. You've probably seen this one before in a previous class. But we're going to come down here and we're going to talk about the same type of thing in a little bit different way. So we focused on 3 different types of functions so far in the courses that we're teaching here. We've talked about linear and exponential, and we've also talked about quadratic. Quadratics are a big, gosh, that's horrible writing. So we'll write it like this, make it a little bit better, quadratic. So we've talked about quadratics. That's the main focus of this course. And when we talk about a function is a consistent mathematical rule where each x, each thing that we put into a function, corresponds with only one y. So every time you give an input, it gives you only one output. We don't get 2 different answers. And we've modeled functions using graphs and equations in this course. And in a previous course, you did sequences like I was talking about before. So let's talk about linear sequences, linear functions and exponential functions and quadratic functions, and see if we can find some relationships here. So linear functions can model, the word is arithmetic. Okay, so write the word arithmetic sequences. And arithmetic sequences have what we call a common difference between each pair of successive terms. So when I go through and I take a look at this one, we've got 1, 3, 5, 7, 9. So the kind of like the sequence that we had up above. This is a linear operation, because in between each one of these, what we're doing is we're adding 2, and we're adding 2, and we're adding 2, and we're adding 2. This is a common difference. Again, the reason we call it a common difference is in order to find this first difference, which is what we call that, then we're going to do 3 minus 1, that gives us a 2, and then we're going to do 5 minus 3, that gives us that 2, 7 minus 5, that gives us that 2, and so forth. Okay, so that's a first difference. So the difference is constant. It's the same every single time. So I'm going to write the word constant right here. So the original sequence of numbers is linear, and then if we find the first difference, those are constant. Those are the same all the time. Now we'll take a look at exponential functions. Exponential functions are a little bit weird. They can actually model what we call geometric sequences. And geometric sequences are different. We don't add or subtract. We don't have a common difference to get from one to the next. We have what we call a common ratio. So the common ratio we'd get would be by taking any term and not subtracting the one before it, but dividing it. So we would do 3 divided by 1, and we'd end up with a 3. So they don't have a common difference, so I'm not going to bother writing that right here. But we do times by 3 to go from here to here, times by 3 to go from here to here. If I take 27 divided by 9, that ends up being 3. So the common ratio on this one is a 3. So again, it's called a common ratio. And that's the ratio between every successive pair of terms. Again, I take 1 divided by the one before it. Now we're going to come back and we're going to look at each one of these. This one in particular, once we know what a second difference is. So I'm going to come down here and let's take a look at what happens when we have a quadratic. We don't study quadratic sequences in any depth or anything like that. We usually just stick with arithmetic and geometric sequences, again, modeled by linear and exponential functions. But we can find the first difference. And let's go ahead and do that, and we'll notice something about it. So again, the first difference is just the difference between every successive pair of terms. So I'm going to do 4 minus 1, and we end up with a 3. I'm going to do 9 minus 4, and we're going to end up with a 5. And 16 minus 9, that's going to be a 7. And 25 minus 16, that's going to be a 9. Well, that's the first difference. And you'll notice that it's not constant. So this first list of numbers, these are quadratic. So I'm going to go ahead and write quadratic. And the second list of numbers, you might recognize it. It's like this list of numbers up above. Let's go ahead and find the difference between the differences. So that's the second difference, or sometimes we call them first level differences and second level differences. Well, this right here would be 5 minus 3 would be 2, 7 minus 5 would be 2, 9 minus 7 would be 2. So the second difference is constant. So you'll notice what happens here. There's this kind of cool pattern with these. It's quadratic for the original list of numbers, and this first difference, those are actually linear, and then the second difference, those are constant. Okay, so we go from quadratic to linear to constant. So linear to constant, and you can imagine kind of up above that would be quadratic if you want to think of it that way. So the first thing we have to do is we have to find the first and the second differences like we just did. And the second difference is the difference between the first and second numbers like we found right there. And the second difference is, let's go ahead and write this down because we found this, the second difference is constant. If that second difference is constant, then the original list right here can be modeled by a quadratic. Now, we're going to do mostly just looking at these patterns and finding differences on these little patterns down below. But what I want to do is I want to come back here and I want to take a look at something. So on this one right here, you'll notice if we find the second level difference on this one, 2 minus 2 would be 0, 0, 0. So the second level difference on this one would be 0. It's just the same, just no difference at all. If we did the same thing here, the third level difference would be 0. Okay, so if we wanted to write something down there, we could. That doesn't happen with exponential functions. It doesn't happen with geometric sequences. So I'm going to zoom in on this one just a little bit so we can take a look at this, just explore this a tad. So I'm going to find the first level difference here. So I'm going to do 3 minus 1, and I end up with 2. I'm going to do 9 minus 3. We end up with 6. I'm going to do 27 minus 9 is 18. I was thinking ahead to the answer. And then 81 minus 27, that's going to be 54. Okay, well, you'll notice that there's no consistent pattern here. So let's find the second level difference. Let's do those. This is going to be, let's see, 6 minus 2, that's a 4. 18 minus 6, that's a 12. And 54, make that look right, 54 minus 18, that's going to be a 36. So with exponential sequences, with geometric sequences or exponential functions, you'll notice that when we go from term to term on the original one, we had a common ratio of 3. Well, what's kind of cool about this is there's no consistent pattern here between the differences, but if we take that same ratio, 2 times 3 is 6, 6 times 3 is 18, 3 times 18 is 54, and that same ratio exists for every one of these, every one of those level differences. So we times by 3, times by 3. So it's really kind of cool that that common ratio exists through all of those differences. So we're going to come down here, and you have a few problems like this on your assignment, and then the back side's going to be a bit different. So let's take a look at this right here. It says determine if the pattern would be modeled by linear, exponential, or a quadratic function. So it's got to be one of those 3, and let's just write down what we've got here. There would be 1 here, or I'm actually going to write it down below. So there would be 1 here, 1 block in that pattern, 3 blocks in this one, 6 blocks in this one, and there's 6 plus 4, so this would be 10. So I don't recognize it right off the bat. It's definitely not linear because if we find this first level difference, it's not going to be the same. So 3 minus 1 would be 2, 6 minus 3 would be 3, 10 minus 6 would be 4. So now we can see a pattern in this. Let's come down here and let's find what the second level difference is. Second level difference on this one would be, let's see, 1 here and 1 here. So because that's constant, if that second level difference is constant, then the original one is quadratic. So I'll just write quadratic on this. Okay, so there's our answer there. Now, the thing I don't want anybody to confuse is this isn't a difference right here. This is the original one. So maybe I ought to write that in a different color on the next one. So let's take a look at problem B here. Let's see, that would be 9 blocks altogether, except for there's 1 missing in the middle. So I'm going to write an 8 right here. We've got the original 8 plus 1, 2, 3, 4, 5 more, so that's going to be 13 here. And so I've got 13 right here, and I've got another 5, so that's going to be 18. Let's see, make sure I got that right. Yep, that looks pretty good. And then I'm going to change colors to find that first level difference. First level difference here, 13 minus 8 is 5. 18 minus 13 is 5. So again, we've got a constant first level difference here. So this one's going to be linear. Okay, so constant first level difference, that's going to be linear. Let's take a look at this one. We've got a 1. Again, I'm going to change colors so we don't confuse those. That's a 1. There's 2. There's 4. Altogether, there's 8. And then we'll go through and find the difference. That's a 1. That is a 2. That is a 4. So let's find it again. This is a 1, and that's a 2. And take a look here. We're seeing that same pattern show up again. So you'll notice, and you may have caught this quicker than I did, we're actually multiplying by 2 every single time. So if I do a common ratio, 2 divided by 1 is 2, 4 divided by 2 is 2, 8 divided by 4 is 2. So this one is going to be exponential. So I'll just write exponential here. So we've got somewhere we've got pictures. Now we've just got lists of numbers. So this is nice that they provided them for us. So I'm going to zoom in just a tad on this. And it says there's a star by this. If there aren't enough terms, see if you can continue the pattern to find some more. So let's just see what happens if we find the differences here. So 18 minus 10 is 8. 28 minus 18 would be 10. Well, we can kind of see a pattern here. So the difference is 8, then 10. If you had to take a guess, the next one's probably 12. So if we added, this would be 40. So let's see if that looks right. Add 8, add 10, add 12. The next one in the list would be add 14. So the next one would be, yeah, would that work? Yeah, we can kind of go backwards here. Yep, so we kind of built up to get this one. So yeah, that looks pretty good. Again, we can clearly see a pattern here in the first difference. So I'm just going to write first here. And then on the second level difference, 10 minus 8 is 2. That's a 2, and that's a 2. So on the second level difference, because that's constant, that means it's going to be quadratic. Okay, so I'll write quadratic right here. Now, you've got the advantage of being able to see your whole paper, so I'm going to shrink this down here and take a good look. So notice that second level difference, here's the first level difference on this one, so I'll write first here and second here. The first one's not the same, but the second one is constant, and if the second one's constant, that's going to be quadratic. If the first one is constant, then the original function is going to be linear. And this one here, the exponential, that's kind of the oddball. They just have the same ratio between each pair of terms when it's exponential. And then this one, again, the second level difference is constant. So if the second level difference is constant, kind of back here to the original one, then that's going to be quadratic. So kind of unique that that ends up being 2 on each one of those. So interesting. Wonder if there's a pattern there. So I'm going to go ahead and zoom in on these last couple. Okay, so almost done with this. Now, if we're going to find the common ratio here, it's got a little star by this, and it says, look for a pattern in each level of differences. So that might be a decent hint. Let's see what happens on this one. This is going to be 16 minus 64. 16 minus 64 that's a negative 48. Okay, so I'm going to better draw those arrows right here. So negative 48. 4 minus 16, that's going to be a negative 12. And let's see, 1 minus 4, that's going to be a negative 3. Well, clearly this is weird because the first level differences are negative. That's because they're getting smaller here. Let's find the second level difference and see what happens on that one. So let's see, this is going to be negative 12 minus 48. So that's going to be 36. And then this is going to be negative 3 minus 12, so that's going to be negative 3 plus 12, so that's going to be a 9. And you'll notice that it's not turning into anything that's constant for sure, but what you'll notice is this is exactly 4 times as big as 9. Or think of it the other way, 9 divided by 36 is 1/4. Negative 3 divided by negative 12 is 1/4. And if I take 1 divided by 4, I get 1/4. Okay? So you'll notice that we have the same ratio. So this one is going to be, I'll just write expo right here, and we'll go ahead and circle that one. And then we've got this last one. Let's take a look at that one. We've got an 8 and a 16 and a 24. Let's just check and see what's going on here. This is 8. This is 8. So the first level difference is constant. We could build another one on here. So if that's 8, this is going to be 32. First level difference is constant, so that means this one's going to be linear. Okay, let's take a look at the other side. Okay, now that we've done a couple of problems where we use first and second level differences in order to figure out, hey, is it going to be linear? Is it going to be exponential? Is it going to be quadratic? We're going to use a calculator for the rest of this because we're going to try and find the equation, the regression equation that fits best. So would it be a linear regression, a quadratic regression, an exponential regression, and stuff like that? I'm hoping that you've seen this in another course. I've got over here what the TI-84 Plus looks like. When you do a linear regression. It looks similar on other calculators. I'm actually going to demonstrate this in a second. These are the steps that you'd go through on a TI-84. The ones for a TI-83, if you happen to have one of those, it's going to be very similar to this. So here's what we're going to do. We're going to enter the data in L1 and L2, and we're going to do that by using the stat button, and we're going to edit those. Again, if there's data already in the list, you use the clear button to delete that data. Please do not hit delete. It will actually delete the entire list from the entire calculator, and then you've got to reset the whole calculator back to factory settings, total reset with that. So be careful with that. And then what we're going to do is we're going to say, I'm going to take the x values, we're going to put them in L1. We're going to take the y values, the f of x values, and we're going to put them in L2. And then we're going to use second mode. That'll take us back to the home screen. And again, stat button, that's going to be our friend. We're going to hit calculate, and we're going to do one of these 3 things. We're either going to do a linear regression, that's usually 4th in the list, a quadratic regression, that's going to be 5th in the list, or an exponential regression. That's at the very bottom of the list. A lot of times it's easier to hit the up arrow in order to find that. So X list is L1, Y list is L2, frequency and store regression equation, those are blank, and then you just hit calculate. So something like this. And again, I'm going to run through and show you how to do this in just a second. And again, I'm hoping this is just a reminder. And another reminder, a regression, when we say something like regression, what it means is return to a former state. So what we're doing here is we're using the data, and then we're going backwards to figure out the function that created that data, or a good estimate of what that function was. Normally, we've got a function, and we produce the data points, the x and y values. It's backwards on this, and that's why we call it a regression. Now, one thing that you really want to catch here is very rarely will we deal with a function that matches the data perfectly. Now, because we've kind of contrived a couple of these examples, we're going to have some that work out really, really nicely. What our goal is to do is to just figure out which of these models is best going to fit that. And we're going to use the calculator and all the sophistication that it's got and all the power tools and everything in order to figure this out. So it says in example 2, and we've got 4 problems here, it says determine if the data is modeled best by a linear, exponential, or quadratic function, and then find the regression equation, and it says round to the 100th when necessary. So the calculator is going to be pretty accurate. It might give us some big, long, ugly decimals for, say, the slope or the y-intercept or the base of the exponential or something like that. We just want to round to the nearest 100th. So if we take a look at this right here, you'll notice that, gosh, it does not look like there's a very good pattern here. And we could spend the time going through something like this, and I'm actually going to do this on just this one. So I'm going to do 9 minus 1, so that's going to be an 8. 23 minus 19, so that's going to be a 14. 43 minus 23, so that's going to be a 20. And then 69 minus 43, that's going to be a 26. And I bet I can guess what the next one's going to be, because what we're doing here is we're going up by 6 every time. So I'm guessing this is going to be 32. And if you did 101 minus 69, it's going to give you a 32. And take a look at this. Now, this is one of those rare ones because we made this up, that this second level difference is going to be absolutely perfect at 6 every single time. So this is constant, so that means this is linear. That means the original one had to be quadratic. So we're going to say quadratic, and I'm just going to put this off to the side, okay? Just put a little circle around that. We know that it's going to be quadratic, but this very seldom happens. And you know, say these numbers were a little bit off. Say these were from real data. This might be, you know, a 9.3, and this one might be a 22, and this one might be a 44.6 or something. So this is going to work out really well. But what I want to show you is on this nice example, let's talk about how we're going to use the calculator to do this. So it is very helpful when you've got data like this to look at a scatter plot. So that's the first thing we're going to do to help us figure that out. And we could run through all of these right here. Again, I'm hoping that you've seen this before. But we're going to use the stat plots, and we're going to do a scatter plot. That's a first one right there. We're going to take a look at each one of these using a scatter plot. So I'm going to pull up the calculator right here, and let's put the data in. Now, normally we have an XY table. So here's the X, and here's the Y, and it's vertical. So that's what we're going to do here is we're going to put that data in. So the first thing I'm going to do is I'm going to hit second memory, and then a 7, 1, and a 2. That's going to reset my calculator. Go back to the home screen, and then I'm going to hit stat and edit. So stat is right here, and I'm going to edit right there. So this is going to be the list that we go to. So I'm going to type in a 1 and a 2 and a 3 and a 4 and a 5 and a 6. So what I've done here is I've just typed in that first row. Those are all the X's. And then I'm going to hop over into the next column. So again, we're kind of doing this vertically like we're used to instead of this horizontal business. So we do a 1 and a 9 and a 23 and a 43 and a 69 and a 101. And we've got them matching up, so that's kind of nice. And then we're going to go to stat plot. So second y equals goes to stat plot. And we're going to turn the stat plot on. And the cool thing about this is you really only have to do this once. So we're going to turn it on. By default, the very first type of display that's selected is a stat plot. L1 and L2, that's the X list and the Y list. So are the X's in L1, the first list we put in? They are. And are the Y's in L2? They are. And then you can use whatever mark you want. That's just the default one. Now, what I'm going to do is I'm going to hit the zoom button. And we probably don't want to graph this in just a standard window. When you're doing stat plots, you want to make sure that the data that you display shows up there. The quickest way to do this is to hit the zoom button, and then you can either go down or you can go up. I don't think it matters on this one. It's actually number 9. Okay, it's a zoom stat. So if we were just on the zoom button, so if I hit that and I hit the number 9, there it is. So it looks something like this. Now, this looks like it could be, I mean, that could be quadratic. Maybe we don't see the other side of the parabola. That looks like it could be exponential. I don't think it's linear because we've got that nice bend to it. So let's have the calculator find out what this is. We've got this evidence right here that it is actually quadratic. So let's just do a quadratic regression. So we're going to hit the stat button. Then we're going to come over to calculate, and we're going to do, we think it's a quadratic, so we're going to do a quadratic regression. Now, if we come down here, you'll notice that number 4 is linear regression, Number 5 is quadratic regression. And again, the quickest way to get to exponential regression would be to hit the up arrow. But there it is right there. So quad, we want quad regression. We want that one right there. So I'm going to hit number 5, or just hit enter once I'm on that. And notice that it says, is the X list L1? Is the Y list L2? Frequency is going to be blank. Store regression equation, that's going to be blank for right now. You might get sophisticated down the road and learn how to do that. We're just going to slide down and we're going to hit calculate, and here's what it does. Now, in an instant, okay? So appreciate what this is doing for you. It actually says, hey, here's the answer. Here are the coefficients in standard form. So by default, it puts them in standard form. So we're going to write y equals 3 for a, so this is going to be 3x squared. Negative 1 for b, so that's minus x, and then a negative 1 for c, so that's a minus 1. So there's the answer. We don't have to like do what we did before, where we're taking roots and plugging them into a function and figuring out, different values and stuff like that. It just spits out the answer and we're all set to go. So I'm going to leave the calculator up right here and we're going to look at this one. The thing we want to notice on the next one is this. We've got the year, and the year is 1990, 1995, 2000, 2005. So this is going up by 5 every time, but this is a common little trick that people will do. Rather than put this in for the x and this in for the y, we're not going to do 1990 for the first x and 1995 for the second one. What we're going to do is we're going to say this is going to be represented by a 0, and then everything else is going to be the years after 1990. So this is going to be a 5, this is going to be 10 years after 1990, 15 years after 1990, and 20 years after 1990. So we're going to go back here, we're going to hit Stat, and we're going to edit. And I'm going to hop up on L2, and I don't hit delete, I hit clear, and then I hit enter, and it wipes that out right there. So hop over on L1, we can see that list down there. We're going to hit clear, and we're going to hit enter. So we're going to type in 0, we're going to do 5, 10, 15, and 20. And we got those in there, got them all. There's 5 values there. We're going to come over here and do 285. 802, 2259, make sure I got them right, 6360, and while we're talking about it, it's really important that you double check and make sure that you got everything in the calculator correctly, because if you don't, you're going to get the wrong answer, even if it's just off by a few. So I've got the right x values in there, 0, 5, 10, 15, and 20, and then let's come over here, 17, 904, yep, 6360, yep, 2259, 802. Now, before we have the calculator display this, I want to take a look at this and see if we can figure out what's going on. Again, this is probably not going to be exact. It's definitely going up, so it could be any one of the 3. This is about 300, and that's a little less than 900. So maybe if I tripled it, and if I triple that, that would be 2400. Triple that, that'd be 6600. Triple 6,000, that'd be 18,000. This kind of looks like it might be an exponential, but not quite sure. Definitely not linear, because this one goes up 600 and then it goes up 1200. So that definitely not linear. Again, we're going to rely on the calculator most of the time to tell us what model we're going to use, and we're going to do that by taking a look at it. So here's the cool part about this. If I go to second y equals, you'll notice that the plot is on and it's using L1 and L2. Well, those are the new L1 and L2 we put in there. So it's all ready to plot that. We've got it set up. We don't have to change any of those. And I'm going to hit zoom. And then remember, if we just hit number 9, there we go. Looks like this. Well, that sure looks like an exponential. Looks like it's going up really quickly right here. So we're just gonna rely on the fact that that's going to be exponential. Besides the fact that it looks like we're multiplying by 3 every single time. So probably exponential. So let's go into Stat and Calculate, and we're going to do we think it's an exponential regression. I'm going to hit the up arrow. I can do that, or whoops. There we are right there. Yeah, that was a little bit quicker. Or you can just hit 0 if you want to. So we've got that right there. Just for the heck of it, I'm just going to hit Stat, Calculate, and I'm going to type a 0 in. Hops right there. Top of the page says exponential regression, so we're all set. Is that the X list and the Y list? It is. Those are going to be blank, so we're just going to come down here. We're going to hit enter, and there's what we've got. Now, this is the type of exponent or exponential function that the calculator stores in there. It has a coefficient out front, and then it's got a base raised to the x. So what this is saying is on this particular function, this is going to be a coefficient out front of 284.95. And then the base of the exponential is 1.23. So that 0 clearly isn't enough to bump that up. And we raise that to the x. Okay, let's take a look at the next one here. Let's see. We've got an asterisk by this, and there's an asterisk over here by the 2012. Let's do the same thing we did here. Let's count this as 0. That would be 10. Whoops, I'm going to change colors just so we can keep track of this. So this is going to be 0. 10 years after that would be year 10. 10 years after that would be 20 years from 1972. And take a look here. We skip 2002 and we go right to 2012. So this is 40 years after. So we'd have to be really careful on something like that in kind of inspecting the first level differences and the second level differences. So if we were to take a look at this and notice, this one goes up by this is about 200, so about 500. And that's about 500 in that 10-year span. And this one, well, this is a 20-year span, so it probably ought to go up about 1,000. And you'll notice that it does go up about 1,000. So there's a bit of a common difference here. But let's see, if this is about a little less than 200, maybe times by 3, it wouldn't work if we're multiplying by 3, so like an exponential, because that would be about 2,100, and that's a little bit too big for that. So again, you can see how it's problematic just kind of looking at this real data and figuring out what goes on there. So we're going to come back here, and we're going to say, all right, I want you to graph this data for me. So I'm going to hit Stat and Edit. Again, we're going to clear this out. So we're going to hit Clear and Enter, Clear and Enter. And then I'm going to type in a 0, a 10, a 20, and a 40. And we're going to match up the data. Whoops, hit enter. 40 on the other one. So 187 here, 701 here, 1209 here, and 2241 on that one. Again, double check and make sure you've got the right thing in there. I'm just going to go backwards here. Looks like we're in good shape. Again, the cool thing about this is once you set up the stat plot, we're all ready to go. So we hit zoom and 9 and take a look at that. There's the first one, and that looks pretty darn linear. So we're going to go with a linear model on this one. So we're going to hit Stat, Calculate. We're going to do a linear regression. That's number 4. So I'm just going to hit number 4. All of those stay the same. So really, once you get the calculator set up and get used to it, it's really not too bad. So I'm going to write down y equals, this is going to be 51.33, then an x, and then plus 186.2. So this is our answer on this one. You might think about what that means on the graph. What that means is the slope is 51.33. And that means that these DDT grams, whatever those are, they're going up because that's positive, up by 51.33, and the starting value is 186, okay, approximately speaking. And then let's take a look at the last one. So the last one, we've got 1, 2, 3, 4, 5, 6, so that's kind of nice. So probably some contrived data like this guy right here. And then you'll notice that it's 3, then it's 1, then it's 1, then it's 3, then it's 7, and so forth. We're going to just go ahead and take a look at that. And then I want you to notice down here, there's a line. We're going to fill this one in. So we're going to go to Stat. We're going to hit Edit. We're going to clear this off, hit Enter, clear that one off, hit Enter, and we're going to type in a 1 and a 2 and a 3 and a 4 and a 5 and a 6. And we're going to hop over here, and we're going to do a 3 and a 1 and a 1 and a 3 and a 7 and a 13. Make sure we've got it all in there the right way. Let's see, 13, 7, 3, 1, 1, 3. Okay. All right. So you might remember that exponentials always look something like this. They've got some sort of swoop to them, and they've got an asymptote. horizontal asymptote. We can flip those up backwards so they can go like this. We can flip them upside down so they go like this, but they've got a bend to them. Linear functions are either going up, down, maybe they're flat or something like that. But this one starts off at 3, goes down to 1, stays at 1, and then goes back up. Well, quadratics of the 3 functions, they're the only, I mean, the choice here is it either goes up or it opens up or it opens down. Quadratics are the only function of the 3 that we use where the values can go down and then back up, or vice versa. They can go up and then back down. So our suspicion is that this is quadratic. If you wanted to go ahead and find the differences here, the level differences, that would be just fine. But we're going to go ahead and take a look at the data on this one. So I'm going to hit, let's see, I'm going to hit zoom and 9, and look at that. Certainly not linear, definitely not exponential because that point's up there. So we're going to do a quadratic regression. So I'm going to hit stat, calculate. Quadratic regression is number 5, so we're going to hit number 5. Whoops. Go back here, stat, calculate, number 5. Quadratic regression, 1 and 2, list 1 and 2. Come down here, and I suspect with those numbers, it's going to look pretty darn nice. So quadratic regressions aren't used very often. There's got to be a really good reason to come up with those. So this is going to be x squared because there's a 1, negative 5x because that's the b, and then plus 7. I shouldn't say they're not used very often. They don't come up very often in nature, I suppose. There definitely are places where we can use quadratic regressions. So that's how you use your calculator to do linear regressions and how we can spot patterns and use those patterns and that data in order to come up with a function for that. All right, good luck on the assignment.